It's an honor and privilege to introduce Dr. Dirk Helbing, our first keynote speaker of IC2S2 2024. Dr. Helbing is renowned in the field of computational social science. He is a professor at the Department of Humanities, Social and Political Science at ETH Zurich, with an affiliation to the Computer Science Department. He's also a member of the external faculty at the Complexity Science Hub Vienna. Dr. Helbing's impressive journey started in physics, where he pioneered pedestrian crowds and evacuation modeling. His work helped establish the field of socioeconomic and traffic physics. He holds an honorary PhD from Delft University of Technology and has served as an affiliate professor there, leading the PhD School in Engineering Social Technologies for a Responsible Digital Future. His work is extensively published in top journals like Nature and Science. Professor Helbing is a recipient of numerous awards, including the IDE Swiss Award. Dr. Helbing also helped with co-founding several key centers, such as Risk Center and the Institute for Science, Technology, and Policy, and initiated future ICT initiatives, advancing data science and computational social science in Europe. Please join me in welcoming Professor Dirk Helbing. It's an honor to have you here with us today.
Thank you so very much for the kind invitation, also introduction. I'm so glad to be with you all. So societies are complex. How to manage them? No doubt we're living in a time of big data. And this means within just a minute, enormous amounts of data are being collected. The question is, how much is it really? Are people aware of how much it really is? But for sure, that's kind of the raw oil that goes into the motor that runs the show, and which is AI. And AI has been really taken a phenomenal path. And with this, basically, the idea came up already a couple of years ago that we would see the end of theory. The data deluge would make the scientific method obsolete. And the hope was basically that we could now see what is wrong in the world, and we could basically fix the world where it's broken. And with this, basically, people have started collecting as much data as they could. And the question was, can we now understand everything? Can we understand the human body, brain, and personality? And we'll see how far we have gotten with that. Just to give you an idea of what the side effect is, what kind of data is also being collected is, for example, identifying you with your voice is all possible. It does not even require your own smartphone. It's just the voice pattern that would be used in order to identify you through any smartphone or any microphone nearby. Also, emotional reading is being promoted, and the next thing that's of interest is measuring heartbeat, and then why not EEG? And in fact, we've seen all probably this cover of The Economist a couple of months back, and it has an interesting pictogram over here which indicates that basically our brains would be connected to computer systems. And the question is, how far are we with this really? A couple of years back also, we have learned that brain reading tech is coming, but the law is not ready to protect us. And a crucial role in all this plays the Brain Initiative, which started back in 2013. And here, the goal was to understand the inner workings of the human mind and to improve how we treat, prevent, and cure disorders of the brain, including, by the way, behavioral disorders. And here's an article which is somehow related to this project. And it says, nanoscience and nanotechnology are poised to provide a rich toolkit of novel methods to explore brain function by enabling simultaneous measurement and manipulation of activity of thousands or even millions of neurons. We and others refer to this goal as the Brain Activity Mapping Project. And then also back in 2013, we have learned that soon we would have data volume double not only every 12 months, but every 12 hours. And that would require a lot of storage space for data. It then took a couple of years, and back in 2020, we then heard that the Internet of Bodies is here. And that has to do actually with nanotechnology. And the more professional term for what is going on over here is the Internet of Nanothings, or actually the Internet of Bio-Nanothings. And so the idea is that sensors would become so small they could be distributed throughout our body, in the body's cells. And actually, it would not have even to be sensors, it would be even nanoparticles. And it would be possible to use physics principles to read out data using devices, could also be perhaps a smartphone. And very important in this connection is also quantum technology. As we see over here, quantum computing is quickly progressing. And here it's about combining bits and qubits, but also neurons. And also, I'd like to point out to those who are not working in this field, in this relation, optogenetics is of great interest. And so optogenetics explores ways to stimulate genetically modified nerve cells via light pulses rather than electrically. So besides quantum computing, quantum dots actually play a significant role. Now, also back in 2013, the then CIA Director Gus Hunt said, "You're already a working sensor platform, and it's really very nearly within our grasp to be able to compute on all human-generated information." Now, more than 10 years later, you can imagine how much data that would be and what it would involve. And in fact, for some time already, it's also a couple of years now, there has been an attempt to build a digital twin of the world and its people, and that would involve basically an agent-based simulation of the world and every one of us, and we would be personalized in this simulation. So every agent kind of is simulating the personality of every single person. So given all that data, the question is, can we now fix the world with a control room approach? And in fact, for some time, military, for example, has been working on plans to build a prediction machine. We all know people do all sorts of things. Individual behavior seems not perfectly predictable. So such a machine would also basically attempt to manipulate people's behaviors potentially in order to make the future more predictable. And of course, that would have great advantages in terms of power, among others. But that would also imply that we would perhaps be heading towards a so-called post-choice society. So algorithms would increasingly take decisions for us. And what would we do? That's the question. So could society actually be run like a machine? That's the question that can be derived from that development. And a couple of years back, I've written this book, The Automation of Society is Next, How to Survive the Digital Revolution. And I argue that society is actually not a machine, and optimization is not the right paradigm for society. Anyway, in the meantime, I think we have seen a couple of versions of surveillance-based, data-driven, AI-controlled cybernetic societies. And you can see over here that ranges from smart cities and smart nations to surveillance capitalism over citizen scores and code is law, predictive policing, cashless society, Internet of Bodies, neurocapitalism, and a couple of more. Some people call that big brother or big mother or big other or big whatever society. And one of the paradigms is super intelligence. And some people even call this an AI God. So kind of a system that would know more or less everything and would also be present everywhere and would also additionally interfere with what is going on this planet Earth. Just imagine what a generative AI could do in the future if you feed not only text and pictures into it, but also all the Internet of Things data. Then in principle, it would be conceivable that we would have something like a generative AI for human history. And the question is, would we want this? Would this be a good thing? And then what happened a couple of months ago, is actually more than a year now, so-called godfather of AI, or was he also perhaps the father of the AI god, question mark. He left Google and he warned of dangers ahead. And he was not the only one, actually. Now, from my point of view, we should look into this in terms of feasibility. So can this be established? Can we really build a perfect digital twin of the world, or are there limitations? And I do think there are actually limitations that could be quite significant. We know that ChatGPT and other large language models, they hallucinate. And what would that mean if an AI that runs basically the show on planet Earth would do these kinds of mistakes? There are measurement errors, there are also computational limits, sensitivity effects, butterfly effects, and all of that relates to complex dynamical systems. I will talk about that in a couple of minutes. There's overfitting, there are black box algorithm issues, and a couple of other problems. But in particular, what I think is that digital twins are lacking complexity science as of now. And complex systems need to be designed to support self-organization. And in particular, digital twins would have to be designed in such a way. And I think we're not yet there. That would be a goal. I'd like to remind you also that it's even a challenge to basically understand the game of life with AI. Of course, you could basically come up with an AI system that simulates very similarly looking patterns, but that AI system would probably include millions or even more parameters. While the original rules of the game of life are very simple, they contain very few parameters only. So understanding what generated that data is actually quite a challenge. Moreover, we are now moving, of course, or have been moving from a time where we didn't have enough data to take good decisions into an age where we can take evidence-based decisions. But there is an issue because while processing power increases exponentially, data volume increases even faster. And that means that we'll never be able to process all the data. In fact, the percentage of data that we'll never process increases over time. So there's something like dark data. But there's another issue, which is that complexity of systems is increasing even faster as we go on networking the world. It increases, I think, combinatorially in time. And therefore, something very paradoxical happens that as the complexity of the system increases, even though we have more data than ever and the best technology that we've ever had, we're losing control as we are trying to control the systems in a top-down way. And we need to have a new control principle, which is actually distributed control. And this brings us actually to self-organizing systems. And that's why I'm now talking about complex dynamical systems. And the interesting thing is that those systems behave in very interesting ways. They show self-organization, pattern information, collective dynamics, and little changes of parameters may really lead to completely different system dynamics, as you can see over here for this case of pedestrian dynamics, where you see on the one hand moving people, on the other hand crowds of people standing together. There are actually a lot of examples of complex dynamical systems. And you probably all know them: turbulent fluids, traffic flows, large supply chains, social, political, economic systems, ecological systems, financial markets, group dynamics, crowd behavior, and so on. And importantly, our brain, our immune system, ecosystems, and society are all complex dynamical self-organizing systems. And so living systems and the wonder of life, if you will, are based on self-organization. And it's not a deterministic mechanism that basically decides how those systems change in time. However, there are some interesting side effects. Those systems often have limits of predictability. We know that from weather forecasts. And even if you would have 1,000,000 times more data, we would never be able to predict the weather exactly in 10 years' time unless we do control the weather in all details. And that has to do with the physics of the phenomena behind weather dynamics, which includes turbulence, and turbulence is understood reasonably well. And it means that there are kind of turbulent states where very little changes would create patterns that deviate a lot in the future. And in fact, there are a lot simpler systems that show, in a sense, a similar dynamics. You all know the Lorentz attractor, and you know the butterfly effect, which does exactly this, that while in the beginning the trajectory is nearby, and the difference between the initial situations could be the 10th digit after the comma. After some time, actually, the trajectories will divert, and you will see very different dynamics, and it's very hard to imagine actually that this happens, but there are also mechanical systems that show that kind of dynamics, and one of those examples are double pendula. And as you can see over here, in the beginning, the trajectories would look very similar, but then basically predictability goes bust. And here is a system where we try to control what's going on in the system. It's a Lotka-Baltari system. It's a very simplified version of an ecological system with a predator and a prey. And we assume that there's a hunter that basically tries to get the system into a certain equilibrium, specifically reach this point x1 naught, x2 naught, and that's the red cross over here. But what happens instead is something very different. So now, as you intend to do certain kind of things, the behavior of the system would be very different potentially. And here is another example, well known, of course, where people would try to drive in a circle without producing an accident. And rather than moving continuously as they want, you see a stop-and-go traffic wave forming. And that is because small variations in the speed will amplify. And there is a domino effect that basically produces that kind of phenomenon. Now, the reason for this is that there's a systemic instability. So even though nobody wants this to happen and everyone seems to be in good control of their vehicle and they have good visibility, they're losing control of the collective pattern of behavior. And so the system does something else than what the individuals want to do. Still, interestingly enough, we can actually avoid stop-and-go traffic as we see it over here. We have done that in the simulation that I'm showing you right now. We are starting here with a computer simulation of the stop-and-go traffic that we know. There are simple mathematical coupled differential equations that describe this car following behavior. And of course, we don't want the stop-and-go traffic to happen, so eventually we get mad about the stop-and-go traffic. We'll get out of the car, we'll take a helicopter, and it allows us to see what actually causes that stop-and-go traffic. And it turns out there is an on-ramp over here. And so there are a few cars that are trying to enter the freeway. That produces small disruptions of the flow. Those disruptions are amplified, and that produces stop-and-go traffic. Now assume that we would have, say, 20 or 30% cars equipped with technology that allows self-driving of the cars. And those cars would basically have radar sensors or laser sensors to measure the distances and relative velocities. And they would change their behavior just a little bit. And as you can see over here, that dissolves the entire traffic jam. Even though not everyone is equipped with that technology. And even though there's no control center that controls every single car. So the only thing that we did basically is we introduced a real-time feedback based on real-time data measurements. And so we can say that with the Internet of Things, we can now make self-organization work 300 years after Adam Smith's invisible hand concept. We know Adam Smith's invisible hand doesn't always work, but complexity science and computational social science allows us to make it work. So I'd like to say that complex dynamical systems tend to self-organize. I mean, basically to do what they want, if you wish. But establishing suitable interactions will produce desirable outcomes by itself. And that's a very nice feature. It just needs mechanism design. So we need to find the right interaction mechanism for the system to self-organize in such a way as we want it to happen. So then we'll get the collective behavior that you wish. And there are many other systems of interest that show self-organization of collective patterns of motion. And this includes, for example, pedestrian flows. As you can see, if you have counterflows, there would be the formation of emergent lanes. There's basically a segregation of different walking directions. And also, I should say, however, that this nice, desirable collective behavior does not always occur. There are special situations and circumstances where crowd disasters will happen. And of course, that's not desirable at all. But in the meantime, we understand much better what causes crowd disasters and how they can be prevented. So our understanding of a complex dynamical system really has helped us a lot in order to make mass events a lot safer. We can understand in particular the stop-and-go waves that also occur actually in crowds under particular conditions. Namely, if there's not enough space and there are several pedestrians kind of competing for the same space, then we could have those intermittent outflows. And there's a faster is slower effect. That means that faster people push towards the door, the longer it may take to evacuate that room. On the other hand, we could say in complex dynamical systems, there could be a slower is faster effect. And this insight has actually helped to make progress in terms of chip production. So I've been collaborating with a chip producer in Dresden, Germany, and they had this issue that they wanted to have a higher throughput, but couldn't get there because they have actually tried to accelerate the different chemical processes. And we advised them to do just the opposite. And that allowed for a better coordination of processes. And the result was that they had an increase in the throughput by more than 30%. So quite enormous. And therefore, I'd like to announce that we should actually follow a new paradigm. We should go from control to coordination. And we've done that also in other kinds of systems. So for example, in pedestrian flows at bottlenecks, we often find oscillatory flows. And it looks a little bit like there's a traffic light that controls the pedestrian flows, but it's not. It's just a pressure principle that makes the flow turn after some time. And we get those oscillatory flows basically as an outcome of self-organization. And so we were asking ourselves, can't we use that principle for something? And we decided that we would use it basically to come up with a new traffic light control principle. And you can see it over here. It's able to produce self-organized green waves. I find that quite impressive. Of course, that's a grid system that will go beyond that in a minute. So what are we doing here? We're basically measuring outflows of vehicles from a road section, but we're also measuring inflows. And that allows us to make a very short-term prediction of how many cars would be waiting in the queue to be served by the next green traffic light. So we can calculate how long the green time should be in order to avoid unnecessary stops of vehicles. Now, what we've then done is we've compared several control principles, and the one on the left is what we typically have today in many cities, where we have a traffic control center that acts like a benevolent dictator. It's trying to collect as much data as possible about the traffic situations throughout the city, and then it's trying to come up with the best possible traffic control. Unfortunately, traffic light control is an NP-hard problem, and even for medium-sized cities, that problem cannot be solved in real time with commercial computers, and therefore approximations are being made. But at least there's an attempt to coordinate activities throughout the entire system of the city. In the middle, we have a different approach. I called it the Homo economicus approach. Here, each intersection strictly tries to minimize travel times based on the incoming traffic flows on the neighboring road sections. And there are formulas for that. It's not difficult to do that, but there's no coordination between neighboring intersections. So you'd think we can't be that good. And on the right, we have the same thing, but if there's a long queue, we would first clear that queue before we go back to travel time minimization. And we would think, well, that's nice with regard to the neighboring intersections because it avoids spillover effects, but the focal intersection would actually not benefit from that, and it would even be worse. Now let's see what really happens. Red line is for the top-down control by the traffic control center. As the capacity utilization goes up, the queue length goes up, more or less in a linear way. That's something that we would expect. The violet line over here, this is for the Homo economicus approach, the local self-organization, and it turns out to be much better for low traffic volumes. Because basically we give a green light to every incoming car as it arrives. But you can see over here, then suddenly that curve explodes. And the queue length basically grows beyond any limit. And so basically the self-organization breaks down. It doesn't work anymore. We don't get into this area over here. It would require a traffic control center, we think. However, the blue line over here, corresponding to the other regarding self-organized control, that turns out to be better all the way. And it's kind of surprising, and of course that is for computer simulations, and the question is what would happen in the real world. But anyway, at that time, I think it was back in between 2007 and 10 or so, we were proposing that to the city of Zurich, and there were newspaper articles about it and said there's the revolutionary idea of the professors, traffic flow would control the traffic lights rather than the other way around. So bottom up rather than top down, you could say in a basic democratic way. And however, there was a little article that said, well, what if that traffic light control, the self-organized one, the self-control approach would work too well? Then basically we would perhaps attract even more traffic, and we don't want this to happen. So basic democracy for traffic lights in Zurich, Switzerland, that was a no-go at the time. And then it took more than 10 years, actually, until the guy who was operating Zurich's traffic control center, Christian Heimgartner, was getting together with my previous PhD working on the self-control of traffic lights and established a company. And they had then the opportunity to establish that in Lucerne, Switzerland, another city nearby Zurich. And as you can see over here, those are the green waves that the previous state-of-the-art control system produced. And there's a lot of red here, which corresponds to the traffic jams, the waiting cars. And down there, you see how well the self-control works. A lot of this red area has disappeared. So basically, cars are waiting a lot less. Now, who has to pay for that? Well, interestingly enough, actually, nobody. Everyone is benefiting from this, and quite substantially. So there's, as the city was reporting, there's more green for everyone. And it's only because we're not wasting green time anymore. We're using it much better than before, because we adapt to the real traffic flow rather than trying to optimize and control things in a top-down way. So the conclusion was you cannot control everything top-down. And coming back to future ICT, which was mentioned just before, there was an article in the newspaper which said future ICT turns the world upside down, or the world view, actually. And it says traffic lights control themselves. So it's like, you know, world turning upside down. This is a poster that was made in connection with a talk I gave about the wonderful world of pedestrians. And but perhaps we have to actually look into this. Perhaps there could be something like a Galilean revolution, you know, where basically the change from the heliocentric view to the geocentric view has really changed things a lot to the better and to the simpler. And we may have a similar paradigm shift in connection with the management and control of complex dynamical systems. So I'd like to say informationally assisted self-organization works well. It's efficient and resilient. It can handle reasonable large deviations and perturbations. It's compatible with freedom and with democracy and human rights. And so, given all this, you know, can we make democracy work? And how to do that, actually? Can we use self-organization principle to make our political system perform better? And everything over here is basically trying to make use of collective intelligence. And the question is how to enable that. That is the challenge, because there could also be a madness of crowd, as some people have pointed out. But the goal is to bring the best ideas of many minds together. And there have been, of course, a lot of experiments and also theoretical works about collective intelligence. One of the most important findings, perhaps, is that collective intelligence can often outperform expert knowledge. It can often outperform the best individual solution. And a very nice example for that is actually the Netflix prize, where it turned out that combining the best solution with inferior solution was producing actually better solutions. So we could say diversity wins, not the best. And so, yes, shouldn't we build digital democracy based on the principle of collective intelligence, and how to enable that collective intelligence? And some things are known about it. The process should be actually organized in several phases. And phase one should be independent exploration. That means independent information and solution search. Participants should be diverse and should not be manipulated in their information search. It's actually quite difficult in these days where we have a lot of personalized search engines which manipulate basically everyone. Then in phase two only, there is an information exchange between different people. And in phase 3, then people would sit together and deliberate and try to figure out whether they can combine certain solutions in order to come up with even better solutions. So there would be integrated solution as a result, and perhaps several of them. And that means in the 4th phase, we would have to vote. And the interesting thing about voting is it's very different from optimization. It does not require an agreement on a shared goal function or an average utility function or so. People could have quite different goal functions, and still voting would produce an outcome. Now, unfortunately, most of the time we are using majority voting, and it turns out to be one of the worst voting methods. So if you want to upgrade democracy, we need to think about how it would be best to vote. There are various issues, among them the tyranny of the majority, but also the lack of fairness. And I'm going to talk now a lot about participatory budgeting in cities. So basically about how to distribute a certain amount of money over different projects, a problem that also many companies have. So it can be also applied in companies when you want to invest into, say, future technologies, for example. Now, regarding participatory budgeting, it's about cities, and cities have many districts. And what often happens is that it's mainly the central districts that attract all the projects and all the money, because there's most people in those districts, and I mean there are more voters, and so they can decide where the money goes through majority voting. While in the periphery, there would be very little money spent. And over the years and decades, that would produce social problems. There would be banlieues, for example, and those social tensions can be seen in many countries and cities. And the question is, how can we do it better? So we need we need better voting rules. And so what are the voting rules about? It basically consists of 2 different steps. One is actually collecting voting input. This is how to measure voter preferences. And that can be done in different ways. I will talk a little bit about that. And then all those ballots go into the ballot box. And after that, there's a vote aggregation, and that determines the democratic outcome. There are 2 things that can be changed. One is voting input, and one is vote aggregation. It turns out that this can be quite significant in terms of the outcome. And here's a lot of space for improvement. In order to gain insights, we have created a smartphone app. It's called Vote App. And that Vote App allows to experiment with different kind of voting methods. And I'm just showing you 2 input methods over here. This is the combined approval voting. And basically here people can choose either to approve, corresponding to 1, to abstain, corresponding to 0, or to disapprove, corresponding to -1. They do that for all the options. Then the ballot goes into the ballot box. Another approach is that everyone could actually spread out 10 points over those different options to vote among, and it's possible to accumulate points. So, some options would actually get no points, others would perhaps get 1 point, and others 2 points or 4 points, whatever. You could also give 10 points if you like. So you can express your preferences a lot better. Now this goes into the ballot box, and then basically the aggregation has to be done. And as I said, the most common way is to do majority voting. And over here you can see the first 2 projects will be supported, and then basically we run out of money. This is not the only way to do that. This approach actually ignores entirely the cost of the project. And so there are different ways of doing it. And one other way is basically to look at how many votes a project gets as compared to the project costs. And then you find out that actually there's different projects that would be selected. And a third approach would be that of equal shares, where voters would have a virtual amount of money and they could spread it out over different projects, and every project that collects enough money would be realized. So importantly, those different democratic voting approaches would have different outcomes. And what you see on the left is that majority voting would often produce a result where a single project or a few projects would basically eat up all the money, and there's basically no money for everyone else. And that's the tyranny of the majority, basically. In the middle and on the right, you see that those other aggregation methods actually allow a lot more projects to thrive. That means there are more interest groups that can actually get a benefit, and so more people that would be happy. And I think this is really important in a democracy. So then we actually applied that in a real-world participatory budgeting experiment. Before that, we did a lab experiment to figure out what is kind of the favorite voting method, and that was eventually implemented. It was a process, however, that extended over 2 years or so, and the city was actively involved. They were very engaged, I should say, and they invited the citizens for an initial brainstorming and informed them that would put a pot of money on the table, and people could make proposals what to do with that money. So basically, what they were trying to do is to activate this collective intelligence that we were talking about before. So they were brainstorming meetings using all sorts of digital tools, including Mentimeter, but also others. And so as a result of the first brainstorming round, basically, we had quite a few projects that were put on the map using sticky notes, kind of simple. Of course, you could also do that digitally. And then this process of participatory project formation was actually going on several times. So there were several meetings, and as you can see over here in the beginning, there were more than 100 ideas proposed. And that was eventually narrowed down because some ideas turned out to be not so good. So some people withdrew their ideas, and other people decided to join other teams. And so basically several ideas were merged together. And then there was eventually a feasibility check and so on. And as a result of all those different steps, those projects became a lot more concrete. And there was a collection of 33 projects that finally were judged to be feasible, and they were put to vote. So that's basically what you can see over here. And then the citizenship was invited to do the voting, could do that digitally, but also with ballot boxes, and people were informed through newspapers, but also at bus stops and museums and marketplace and so on. So they were really trying to mobilize people, and there was actually quite a lot of interest. And this is the outcome over here. So you can see over there, the red dots correspond to projects that were chosen, and those are characterized by having particularly many votes as compared to the project cost. Now here we see a comparison between what would have happened with majority voting and what happened actually with the new voting approach that we have implemented. There was 10 points distributed over projects, and then a proportional fairness approach. So on the left, majority voting would have selected only 7 projects, and all of them would have been located centrally. Most of the city districts would have received no money. Instead, on the right, based on the proportional fairness approach, there were 17 projects that were selected. And every district actually got some money and some project approved. So you can imagine that people were a lot happier with the outcome. And there's another interesting point that people were actually very much engaged, and the process was a lot more inclusive than usual. I mean, in Switzerland, there's a lot of voting. They vote actually also on referenda, not every 4 years, only for a parliament. But as compared to those referenda, we had some benefits because it turned out that more elderly people were actually participating in this process. Also, more young people, more women, also more foreigners. And so it was a lot more inclusive, and there were a lot more people basically benefiting from this because there were 17 projects selected rather than 7. So I'd like to conclude that democracy can be upgraded. There are more projects that can be realized because the approach is more resourceful, considering that not only the number of vote counts, but also the budget that it costs. People are a lot more careful in terms of demanding money. Then there's more participation, more inclusion, more transparency, more trust, more satisfaction, and more fairness. And I'd say it's very different from an optimization approach. An optimization basically tries to maximize a one-dimensional goal function. Here we have many different goal functions. This approach is a lot better for pluralistic system as democracies are. So I'd say one should implement more democracy, not less. And then the question is, can we actually upgrade the economy too? And according to Elinor Ostrom, actually self-governance would be efficient if proper design principles would be applied. So how can we combine synergy and cybernetics in a way that would be enabling self-organization? And that brings us to synergetics, actually. So in fact, over the years, decades even, I should say, we studied, and based on digital assisted self-organization, we found solutions for coordination, cooperation, collaboration, co-evolution, conflict, crime, pedestrian flows, traffic congestion, crowd disasters, and economic systems. So assisted self-organization, that is kind of the approach. And here, digital technology actually can make a big difference in terms of mechanism design. So we all know that we should be a lot more mindful about limited resources on planet Earth and how could we get more sustainable. Everyone basically agrees that it would be nice if we had a circular economy. We would reuse a lot more resources, and we would waste a lot less resources. And the question is how to get there. And so far, we've been trying to do that basically by regulation and in a top-down way. We haven't made that much progress, I would say. And so how else could we proceed? Well, I think we should use the Internet of Things, but we should use it in a different way. We should use it in a participatory way. So we should have an open participatory Internet of Things, and that would allow us basically to map noise and other externalities, CO2, temperature, noise, and all sorts of materials that could be recycled, and good things and bad things, good things like education, culture, and so on. Everything in principle could be measured. And then what you'd like to do is to increase positive externalities, reduce negative ones, and ensure fair compensation. And so, inspired by what nature does, what happens in ecosystems, which are basically recycling systems, we have come up with the idea of a socio-ecological finance system, which we call Fin4+. And it's combining basically the Internet of Things with blockchain technology. doesn't have to be blockchain technology though. But the point is here that we would have different kinds of money. And that means we could establish different kinds of feedback loops locally based on measurements. So different kinds of measurements would basically define different kinds of currencies. And that would allow us to establish new kinds of incentive systems, multiple incentive systems, not just profit. And so this way we would introduce new forces into our economic system. And those forces would basically incentivize that everyone makes little improvements given the situation around them. And everyone would respond to those little improvements. And as a result, it would be a co-evolutionary process that would improve the circularity and the sharing in the system and would make the system more sustainable, as it happened in biological evolution in the ecosystem that I mentioned before. I do think that a multidimensional approach is a paradigm change, is really important. We know that typical supply networks today look like this. They're pretty hierarchical, pretty linear, even though networks. But typically, you try to avoid feedback loops because that reduces apparently controllability. But you don't need controllability. You just need to have a working self-organization, and that requires feedback loops. Look at how nature organizes things. So this is a typical metabolic network. So we could also view that as a supply network as we find it in nature, and it looks completely different. There are a lot of cycles in that system. And of course, when there's a cycle, I cannot anymore say, is A controlling B or is B controlling A? In principle, they're influencing each other. And that is the paradigm that basically coordination replaces control. And so we could say that network effects make all the difference. I think we're seeing a transition from a component-dominated view of the world towards an interaction-based view of the world. Collective intelligence could be used to improve our democracy and society. Multidimensional real-time feedback could be used in order to make our economic system a lot more sustainable. And so I'd like to invite you to think about this and to be a game changer and basically to contribute to building the next civilization using digital technology, but in a participatory and democratic way, using self-organization as a bottom-up principle to allow self-organization to control the system in a favorable way. So yes, I would say it would have been a great idea if the US would have implemented a future ICT project based on self-organization. With this, I'm at the end of my talk. Thank you so much for listening, and I'm very much looking forward to your questions and comments.
Thank you so much. We really enjoyed it.
Glad to hear that.
Thank you. We have a couple of questions in the chat. Do you prefer me to read them or?
Yes, I think that would be great.
Awesome.
Because I don't see them right now.
Sure. So the first question that we have, it says, although the society is a complex system, it might act linear in terms of a small time scale. So prediction based on digital twin would be valid in that time scale. Also, it is good to know that many other complex systems, but pedestrians, system, and democracy might have different degree of complexity. So to figure out the degree of the complex of the system, is there any measurement, some kind of Lyapunov exponent of the society generally in social sciences?
Yeah, these are very good comments and questions, actually. Yeah, the Lyapunov exponent is, of course, one of the measures that have been used in chaos theory and complex systems a lot. I'm not sure how far that actually is useful in the context of measuring complexity of society. For me, the question is, what happens after the linear part of prediction? And do we want to have a completely predictable and controllable world, or do we want to live in a world that allows for good things to happen by chance, like serendipity, and where innovation and creativity is possible? Or do we want a world that works more like a clockwork in a mechanical way? I personally think that it has benefits if we allow for those unexpected things to happen. We know that from evolution, there are mutations, and mutations basically drive all the progress. Of course, not always do the mutations produce good things, so it needs to be combined with some other mechanisms that select the better solutions and make them spread. Well, we know a lot about how to do that. And I do think that I'd like to live in a world where we'd like to contribute all with our skills, with our knowledge, with our ideas, and would like to be able to co-create the future and our neighborhoods and our workplaces. And that's what I care about. Agency should have a place, and that requires that we have a participatory approach. And that couldn't be done in the past on a large scale. When many people were involved, basically, the systems didn't scale and it took a long time to take decisions. And we have now found some approaches, I couldn't report all of that today, where we can basically make participatory systems on a large scale a lot more efficient and scalable, including, by the way, co-creation process and evaluation of all those different potential solutions that people would come up with. We have a web page on our publications on digital democracy, and I recommend to have a look at it and get inspired and perhaps even collaborate. I think there's a lot of interesting work to be done.
Awesome. Great. The next question is from Giovanni. First, they said that it's great to see you and thanked you for the great talk. And then they asked, you mentioned how these interventions can sometimes be opposed and fail to be adapted due to distrust that they would work too well. For example, the city of Zurich with traffic lights. Do you have any suggestions on how to overcome this issue and improve adoption of these type of pro-social interventions?
Yeah, I do think we need to collect the experience with those approaches in order to build trust, because it's really a paradigm change. It's requires to change our thinking about the systems in the world we're living in. And that will take time, most likely. But we don't have to wait for our government to do that, because very similar approaches can actually be implemented in any company and any team. Now, where decisions need to be taken, do we do this or do we do that? And the question is how to decide that. And, traditionally, that has often been done in a top-down way. I think that is now changing. I'm observing that young people want to go about it in a very different way. And then, of course, that doesn't always work out, because there could be potentially a lack of coordination. So that's why we need to collect experience on how to make this coordination and collective intelligence happen. And I do think that these are really exciting times where we're learning how to make use of the wonders of nature and this world of the wonder of self-organization to let it play out for us.
Awesome. And maybe our last question, since you're on top of the hour. Thanks for the great talk, Arya said. What are the best ways to gain public trust in such frameworks? It's one thing to introduce such systems, and it's another thing to persuade the public to put their trust in them. How can we facilitate the process of adopting these digital democratic systems with different societies, given the diverse population of countries like US?
My impression is that we've gone through a couple of different digital society frameworks. I showed you one slide where I presented, citizen scores and surveillance capitalism and neurocapitalism and all of that. I think basically we have tried it more or less all. It hasn't really worked in a convincing way. It doesn't change the world in a way that makes us feel better about it and very optimistic about the future. We're waiting for the environment to develop in a much more favorable way to find a balance with nature. We still have problems with our financial system. We have problems, of course, establishing peace. That's perhaps one of the greatest challenges right now. I do think they're wonderful technologies, and we can make fantastic use of them, but they could also be terribly misused against people. And so in order to make best use of all those technologies and data that we have now, we first need to establish world peace, and that's kind of the number one challenge. And once we have managed to do that, I think we can go forward trying new things, knowing that we have tried out everything else and it didn't work. So, digital democracy is next.
Awesome. Thank you so much. I think since we are over time, if you have more questions, please reach out to us. We'll definitely make sure to share that with Dr. Helbing, or you can directly reach out, I think. We really thank you for joining us online, taking the time, sharing your amazing work with us. We wish you were here in Philly with us, but thank you again for taking the time to present your amazing work. Thank you again, and to everyone who attended this talk. We really appreciate it.